Work. All right, let's, if this pops up, then we are in business. Oh, looks good. Nice. Okay, so welcome to our second review session. Thanks for joining. If anyone's tapping in at home, I don't actually think anyone's going to watch. Even last time, I think I had 3 people viewing. There were 4, and one of them was me. You know, I'm streaming my own review session right now so that I can see it up here, and that'll give me access to the live chat. So let's go ahead and get started. We've already asked a couple questions about the format of the final. We've gone over that, so we don't need to rehash that. We've talked about that quite a bit in class as well. So are there any other questions about kind of the format of how things are going to look the rest of the week? Or do you want to jump into some content stuff?
Can we go over like this type of thing that we did in the station?
That type of thing, we sure can. So that type of thing, we've got a person in free fall. They have a weight, and their weight is not going to change, right? That W vector, that force of gravity down is not going to change. The thing that is changing on that person is their force vector up, which is going to be from air resistance. So when they first jump out of the plane, right, they have a force gravity of 1,000 newtons, and they have air resistance force of 0, right? They haven't sped up enough for air to really be slowing them down. What's their net force? 1,000. So I think the activity today said, let's assume his mass is 100. So then what's his acceleration?
10 meters per second.
Yeah, we're going to use F equals ma, and we should say F net equals ma. So we're going to say 1,000 newtons equals 100 kilograms times A. Well, 1,000 over 100, A equals 10 meters per second squared.
What's the difference between F net and Fn?
Fn is normal force.
Which is
just your force perpendicular to your surface. Fn is actually a force that you can draw on your force diagram. Don't ever draw net force on your force diagram unless it asks for it, because I don't want it to confuse you. So then, after a little bit, this guy, his force of gravity is still 1,000 newtons, but now air resistance force is, let's say, 400 newtons. So what's our net force? 600. Then we do the same thing. So A is 6 meters per second squared.
So the ones where it's like 1,000 and 1,000 where they're opposite, then that's when he starts to have negative acceleration.
Well, if I have 1,000 down and 1,000 up, what's my net force?
0.
0. So 0 equals m times a. What does a have to be?
0.
0. So that's when I have no acceleration. That's when I have reached what? Fancy word for this. Nope. Terminal velocity. When my force of the air resistance upward is equal to my force of gravity downward, I've reached my terminal velocity.
Did we mention that in class?
Yeah, I think it's also in the book. The whole section on free fall, I think is when we're talking about that. Then, after we hit our terminal velocity, there's another one where then he releases his parachute.
So is that when you'd have a negative acceleration?
Yeah, that's when F of air is 1,200 newtons, and your force of gravity is still 1,000 newtons. So now all of a sudden, what's our net force? Well, it's not negative. It's just 200 newtons up. So we're going to use F net equals ma. We're going to say 200 equals 100a. So now a equals 2 meters per second squared, but now it's in the other direction. Now this is up. Notice that all of these accelerations are going to be down.
So would you make it negative or no?
No.
You just...
There aren't negatives here. It all has to do with your direction. You never have a negative acceleration. You just have an acceleration in the opposite direction. That's why, and you can never have a negative force. There's just straight up no such thing as a negative force. It has to do with the direction that your object is traveling in. Okay, let's see what we got. I just want to make sure that, okay. So does that explain what's going on here? Really, it should be very plug and chug, very much like you just finding your net force, plugging that in for your acceleration, move on to the next one. You good here?
Yeah.
Okay.
Could you explain terminal velocity again for me?
Yeah, so terminal velocity, I mean, it's got velocity right in there, and terminal kind of means like at the end. So terminal velocity is the highest velocity you can reach, and generally it's when we're undergoing free fall. But if you are in, sometimes we talk about terminal velocity with really fast cars, because there's going to be a point with anything that goes really, really fast, eventually you're not going to be able to accelerate anymore because the force that you have, in the direction of travel, in your direction of motion, is going to be opposed by an equal force of the air resistance. So those air particles basically blowing into you, trying to slow you down a little bit. So terminal velocity, for our purposes, let's just use free fall, it's when our force of gravity, our downwards force, is counteracted entirely by a force upward by the air. So if we think back to like the hammer and the feather example, it's not that a feather accelerates any more slowly due to gravity. It's that the feather isn't going to speed up as much because it accelerates to its terminal velocity so quickly. That force of gravity down is counteracted very easily by a force of air resistance up. Whereas something like a hammer or a ball or a piano, that is going to accelerate downward at 9.8 meters per second squared. And it's going to take a lot more work for that air resistance to build up enough force upward to counteract that force of gravity down.
Can we go through like all the laws, Newton's laws?
Sure. I'll do this real quick and dirty. 1, inertia. And I'll expand on this when we're done. 2, F equals ma. 3, force pairs. 4, what's inertia?
Object will stay at rest.
So that's the law. That is the law of inertia. What is inertia itself? Yeah, yes, you're on the right track. It's an object's resistance to changes in motion. So mass and inertia are very closely related. If something has more mass, it has more inertia. A bowling ball has more mass and more inertia than a wiffle ball. It has more resistance to changes in its motion. It's harder to get moving, but then once you get a bowling ball, whipping down the alley, it's also a lot harder to stop it moving, right? Would you rather bowl with a bowling ball or a wiffle ball? A bowling ball. If you bowled with a wiffle ball, it probably wouldn't even knock the pins over. because it hit a pin and it stopped. So inertia is the tendency for objects to resist changes in their motion. And the way Newton's first law is worded is like you said. An object in motion tends to stay in motion. An object at rest tends to stay at rest, unless acted upon by an outside force. Newton's second law boils down to the sum of our forces, or our net force, equals mass times acceleration. And what I should really put here is this little guy, this sigma. This stands for sum. You can think of this as just F net. That's why we get F net, because it's not any individual force that causes our acceleration. It is our net force. It is the overall sum of our forces that cause our mass to accelerate. So that's what we're looking for there. This third one is what we looked at today in class with our stations, where forces always come in pairs. Action-reaction pairs, we call them. And the way I try to think of it is think of on, by, right? If I am standing on this floor, I have a force of gravity that causes me to exert a force on the floor.
Brett Dirksen to the
Right?
general office, please. Brett
The floor
Dirksen to the general
also
office.
exerts a force back up on my feet. And those forces are equal and opposite, right? I exert a force on the floor exerts a force back on me. And that's what's going on here. And this can get really tricky. We're going to talk about it more tomorrow. But this is really, it gets into some very strange conceptual hang-ups. What we're going to talk about tomorrow is what's called the horse-cart problem. And basically it has to do with how the heck does a horse pulling a cart move if all the force pairs are equal and opposite? Right? Because if everything is always going to be equal and opposite, how does anything ever move? And it is a real stick in the mud. It's tough to wrap your brain around, but what I need you to know for the test and for the final, forces come in pairs. They're always equal and opposite, and all you got to do to figure out your force pair is flip your on by. The force on Mr. D by the floor, the force on the floor by Mr. D. That's your force pair. There's another force pair there, the force by the earth on Mr. D, right? That's my force of gravity. And there's also another force there, the force by Mr. D on the earth. So not only am I attracted to the earth is attracted to me.
How does that work with, like, multiple people being attracted to the earth?
Everyone's attracted to the earth, and the earth is attracted to everyone. We all have force pairs with the earth. And so some people think, well, why doesn't that cause the earth to move? Or what if we had everyone in the room jump at the same time? Well, it's hard to understand exactly how much more massive the Earth is than us. Huge mass. Our mass is, even the most massive of us are probably about 100 kilograms or less. The Earth is on the magnitude of, billions, trillions of kilograms. It's mind-boggling how massive the Earth is in comparison. And you also need to realize, well, you probably don't accelerate upwards more than a couple meters per second. So if you're only looking at meters per second in terms of, the Earth being billions of times more massive, you might be looking at the Earth accelerating, a fraction of a millimeter. And what happens is over the course of everyone moving, everyone walking, that evens out over the course of the day.
So the test on Wednesday is just basically these three laws?
Yep, pretty much Newton's laws. It's going to be finding net forces. It's going to be understanding some of the concepts, understanding first and third laws. Can you use F equals ma? Finding your net force. Sketching force diagrams, basically everything out of the packet, everything out of the homework. Make sure you are reading the stuff out of the book because there's some important stuff in there. but you know, it's kind of all fair game for this test.
I have a question on this one.
Mm-hmm.
How would
Finding net forces?
Yeah, but this one has like an angle in like 3 other directions.
Yeah, so the way we're going to approach that one is it's helpful to use some of the information we found earlier, right? I think we have a 7 Newton, and then a 10 Newton down this way. Well, we found out earlier from one of the ones above, if you take out this 10 Newton one, your 7 and 7 like this is going to give you a net force 10 newtons up and to the right. Well, if I have 10 newtons up and to the right and 10 newtons down to the left, my net force there is going to be 0. Right? If you remember stuff about trig, you're going to have, you know, a 45, and it gives you here that this angle is a 45. So you know that they are 180 degrees apart. They are in exact opposite directions. So you can think of this as like a 10 and a negative 10. And you're going to have a net force of 0 there. So, you know, if you were given this straight away, I don't want you to worry about angles. So I don't think I would give you something quite like this, but I want you to recognize that it's just a matter of doing your Pythagorean theorem for your 7 and your 7, and then seeing that, well, I know if I got this 10, that would be as if I had a 7 and a 7. And if I have a 7 in all directions, my net force is 0.
I'm still having. Can you just go over Newton's second law one more time? I'm kind of so confused.
Yeah, so second law. Newton's second law is F net equals ma. So this is the big thing. You gotta have this locked down now. So whatever your net force is, you're gonna have to calculate your net force to start with. Then, you know, let's say like in the back, station 9, I think it was, where you were just given, you know, let's say I have something with an 8 Newton force and 15 Newton force. What's my net force? I'm going to take my 15, move it up here, look at my triangle. I'm going to have 64 plus 225. 289. I'm going to take the square root of 289, which is what, like 17? No, yeah.
I think that's right.
17.
Yeah. I like to think I know my perfect squares. So that means my F net here is 17 newtons. And that's what I'm going to plug in for here. Now let's say, you know, these are forces that are acting on a 5 kilogram bowling ball. So now we're going to say 17 newtons equals 5 kilograms times A. Well, all I got to do is divide 17 by 5. A is going to be what? 3 2/5? Or 3.4 meters per second squared.
So could you say Newton's second law in like a phrase, like the first and third, or is it not really like a...
If you wanted it in a sentence, I would just say net forces cause masses to accelerate. And that is basically turning this into a sentence. What else we got? Come on. If we got questions, let's answer them.
I was just wondering, because you said inertia is very similar to mass.
Mm-hmm.
How would you differentiate them?
So mass is just how much stuff is in an object. And mass influences an object's inertia, but it is not everything there is. It's kind of like, when we're on Earth, mass and weight take on very similar sort of roles. Like, a lot of times we think of mass and weight as the same thing, but they're not. And I want to be similarly specific with mass and inertia. Inertia is just an object's tendency to resist changes in its motion. Now, that is going to be dependent on its mass, but inertia is not in kilograms. Inertia is just a concept. It's a quality of an object. So it's not like, a 10-kilogram bowling ball has 50 inertia.
There's no unit.
There's no unit. It's just a quality about an object. So, it's just the kind of thing I just want you to understand that the more massive an object is, the more inertia it has, the more resistance to changes in its motion it has. And really, that arises from this, right? If I have a more massive object, I have to increase my net force to have it undergo the same acceleration. That means that the more massive an object is, the more it's going to resist changes in its acceleration, because you require a larger net force. Let's keep it going.
We go over just briefly over waves and
Sure.
Harmonics and.
Did you watch the review from Thursday?
I started to, but I didn't watch it.
Okay, because we went over a lot of the stuff on waves. I'm happy to do it again, but I also want you to know that you can go back and double check that, because maybe I'll miss some. So just in case, go back and look at the video from Thursday, because we talk about a lot of this same stuff. So let's start with labeling some parts of a wave. So I've got some wave here. I'm going to say this is our amplitude, and this is time. So this is an AT graph, an amplitude time graph. I want to label a couple things here. I want to label
nodes and antinodes.
It doesn't really work out very well on this because I don't want to confuse you. We can do nodes and antinodes on a different
Can
thing.
we also do
Can you explain this picture?
yeah, that one, and when you did the tube thing, how that worked when it made the sound with the nodes and antinodes, and the heat and that thing.
Mm-hmm. Yeah, we can talk about that. So let's do this first, and then we'll move to that interference pattern, and then we'll move to the cardboard tube node antinode thing. Okay? So, start here. Where's amplitude?
The x-axis, and it goes up to.
Come up here. Come on, it's just YouTube. You're going to be immortalized on YouTube. It's no big deal. I don't want to be immortalized on YouTube, but here we are.
Yeah.
All right. Yeah, that's amplitude. It's from where to where?
X-axis to the top of the crest.
Yeah, well, it's from our median, right? Our midpoint to our maximum, because it's not It's not that. That's not our amplitude. Our amplitude is from when our medium would be at rest to its maximum position. So good. Where is a crest?
The wave.
Top of the wave, right here. Yep, we've got a crest there. Where's a trough?
Bottom of the wave.
Bottom of the wave. Yep, very bottom point. Crest is at the top, trough is at the bottom. Where is a wavelength?
It's from the distance between crest to crest, trough to trough.
So I want us to be careful because this is tough here. We're given an amplitude time graph. We're not given, this is not like a horizontal distance. So I know that a lot of students are going to want to think that like this is a wavelength. What is this? If I have an amplitude time graph.
Period.
This is period, yeah. Wavelength I cannot get from this graph. I do not know the distance between crests. Okay, this was on, I remember this was on a Physics of Fun. Like everyone got this wrong. And I don't think I spoke about it in class because it's super nitpicky. Because it only matters when you're given a wave pattern that's a function of time. Because normally when I give you a wave pattern, I am specifically saying like, this is what the string looks like. Well then, yeah, then it's easy. Then I know that that's my wavelength because the string is literally right here. But in this case, this is not what the string necessarily looks like. This could be a single particle, right? This could be a molecule of air vibrating up and down in space over time. So you wouldn't be able to calculate a wavelength from this type of graph. Again, super nitpicky, just want you to be careful. So actually, I want to stay on this side so that it shows up on the video. We wanted to look at an interference pattern, right? And you wanted to look at that, was that the double slit interference pattern? I mean, that's really hard to draw, but really easy to explain. So your double slit interference pattern happens because you have this, you have waves that are being fed into this double slit. And so how do waves propagate out of a narrow opening? They radiate out in semicircles as a curved wave. So what we're going to see that kind of thing from this one. Now we want to do the same thing here. Now, of course, this is pretty bad because it's not even. But the idea is where you see these lines, each line is a crest. What happens when a crest and a crest interfere? No, you get constructive interference. You have a crest and a crest. Those are going to interfere and give you a big crest. So wherever I have two black lines, I'm going to have, I don't know, you want to call it a supercrest or something? You're going to have a supercrest. You're going to see a large amplitude there.
And then the areas in between those dots are the destructive thing.
Well, so when I have a white space and a white space, that's going to be a trough and a trough. So that's going to be a super trough. So these spaces are going to be even further down in my medium. Where you get your destructive interference is where you have a crest going through a trough. So like here, 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 here. So you're going to have all of these patterns of constructive and destructive interference. And the idea is, remember that Veritasium video we watched about the double slit experiment? You're going to get these bands. So it's really hard to see here, but you'd wind up seeing these lines, you know, radiated outward kind of from your interference pattern. That's going to give you these bright and dark spots that have to do with where your crests and troughs interfere, where you get constructive interference, and where your crests and troughs have destructive interference.
So when it's a trough and a trough, is it still constructive?
It's still constructive interference, yep, because they're still adding up to give you something bigger, right? If I have that and that, I'm still going to get a super trough. And I guess that's what I'll call it, a super trough. Super crests and super troughs. So the only thing that I really want to hammer about that interference pattern, another thing most students missed, you're going to see these bands, like from the Veritasium video. He highlights those bands. You can go ahead, check that video out again on Power School. You know, I realize that was a long time ago, but I'm sure you can find it. Or you can just go to YouTube and search Veritasium double slit. I'm sure it'll be the very first thing that shows up. And if you just go pretty much to the last like 2 minutes or something, you're going to see where he's making those interference patterns on the water, and then he does the highlighting of the constructive and destructive interference, and that might give you a little bit better visualization, a little bit better idea of what's going on there. And was there something else that we wanted to talk about? I thought there was another question.
Yeah, the nodes and antinodes.
Yeah. Let's do something with nodes and antinodes.
What's the cardboard thing?
Like what?
Like the...
Oh, yeah, you want to do the cardboard tube. Yeah. So here, this marker is on its last legs. So let's look at the cardboard tube. I've got my Bunsen burner inside with my flame. My flame is going to cause the air to heat up, which is going to make that air expand. And that's going to essentially create this wave pattern. So I'm going to have this sort of thing. So this warm air is going to cause a wave pattern. It's going to cause the air to vibrate. And when the cardboard tube is at the very exact right spot above the Bunsen burner, for the top of our tube to get the antinode of our vibrating air, that's when we're going to get resonance. If I bring this tube down to anywhere besides the antinode, we're not going to have resonance. There are some spots, if I bring it down just a little bit, I'm going to get, again, sort of this weird beat frequency sort of thing, where I hear wah, 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 and that has to do with these vibrations sort of at certain points adding up. Now, I couldn't tell you why that sometimes works and sometimes doesn't work. It didn't work for me, and I know Mr. Bergman was able to do that. I could not. But you definitely get that resonance when you are right at the antinode. So, and you definitely don't get that resonance when you are right at the node. Right? If I'm right here, there's going to be no amplitude of that wave. So you can't hear anything if there's no amplitude. Whereas when I am right at the antinode, I am at the maximum amplitude for that wave, so I'll be able to actually hear that. That's actually going to cause my tube to vibrate.
Where are the nodes and antinodes?
What do you mean?
Like on a wave.
Oh, sure. Yeah, so just generally speaking, if we just look at this, this is an antinode.
Wouldn't that be a crest then? Or is it crest?
A crest or a trough. A crest or a trough can be an antinode. And then a node is right there, and then an antinode is right here. And then this is also an antinode.
So are nodes like in between crest and trough then?
I don't really want you to think of it that way, because the way this works is this air is vibrating back and forth all the time. Remember
So
when we did our standing wave pattern on the string? You also have it switching between the dotted line. So it's not necessarily that this is a crest, it's that this is an antinode. It is both a crest and a trough. It is just the point of maximum amplitude.
So an antinode is point of maximum amplitude and a node is where it's kind of staying the same.
Yep, and a node is where we have a point of 0 amplitude, where all the string is going to be doing here is switching back and forth. You know, it's not moving up or down at all, it's just moving back and forth. And it works if you don't have fat fingers, and really it works if you use like tweezers or something, but you can grab the string. You can actually grab the node and it won't affect the oscillation of the string. I think I tried to do that, but you know, with your fingers it's just too fat. Any other questions on waves? Like I said, there was a lot more we did on this on Thursday. We broke down a bunch of vocabulary, looked at some stuff on harmonics. So if you have questions on that, I would refer you to Thursday's video. I also, speaking of videos, I also have Mr. Bergman's review from Friday, but for whatever reason, YouTube pulled his down for copyright, or not copyright violation, terms of service violations. So we're trying to iron out why that happened. And get it put back up so that you can actually watch it for some review. I'll get that link out to you when I can. But for now, just check the video from Thursday.
For pendulums, we just need the equation.
I mean, understand how a pendulum works, right? You've got a length of string, you've got a mass on the end of a bob, or you've got a mass at the end of your string. You call that the bob. And you just raise that up and set it swinging. And the only equation we've got to describe the motion of a pendulum is t squared equals 0.0403 seconds squared per centimeter times L. And L has to be in centimeters here.
So length is the only variable that affects the period of a pendulum. Or is that not?
Is what?
Length.
Yeah. It's the only one in the equation.
Yeah.
Not mass, not amplitude.
On the formula sheet that we're going to be given, the equation sheet, will the squares be noticeable?
I'll tell you before class because I think most of them have been written in, but I'm going to say make sure that's the case because there's no excuse. At this point, you've been seeing it over and over and over on your own equation sheet. So I'm going to say, before the final starts, before the lab practical starts, make sure these equations have squares on your equation sheet. That's your only warning.
Is that the only one that really need a square?
I think in our kinematic stuff, in the d equals 1/2 at squared, I think the t does not show up as squared there either. I think that's all we have for this semester, though.
So we're doing the rest of these equations second semester?
Well, so a lot of these I don't know if we even hit on. We're doing forces and acceleration right now. I think our next unit is energy. I don't know if we do anything with electric forces and fields or thermo or gravity. Maybe we do a little bit with some of that, but I think that's going to be very close to the end. I'm also not sure what we cover with relativity. But we'll see. I think most of this depends on how far we get towards the end of second semester. We don't have a lot of viewers right now. I think I'm the only one watching.
Yeah, I looked up for the task.
Oh, that's fine. I mean, you're right here. You don't need to be watching it. So yeah, I think on here the only squareds that don't show up are that t squared, and then the t squared in d equals 1/2 at squared. And then technically the x equals x naught plus v naught t plus 1/2 at squared, the square doesn't show up very well either. But we haven't really used that equation. That's a little bit more for AP.
Will we be able to use this sheet on
No.
the... No.
Well, we have to use stuff like that for the final, or are we not really looking at it?
It's possible. I guess just so that I have it on video, they were asking if they need to know the graphical methods sheet, how to linearize our graphs, and I said, that might be included. You will not be able to use that sheet on the lab practical or the final exam. For both the lab practical and the final, all you will be allowed to use is a calculator and your equation sheet. You can use scratch paper if you want to do some scratch calculations or something. That's what you'll be allowed to use.
Will the lab practical be like an actual test type packet?
Yeah. You'll have, I think I'm going to have like a sheet for each station. So I'll probably give you like a packet, and each page will be one of the stations. So since there will be 5 stations, you'll have, 3 pages front and back, and you'll just, you'll be writing down your answers and showing your work as necessary for each of those lab practical stations.
Do we have to use DGAS?
Yep.
For every single one?
If you need to be solving an equation, yes. If it's a situation where it's like, read this, or like dissect this data table, dissect this graph, tell me what this value is. If I gave you, like, let's say I had a position time graph that was like this, that was, an object accelerating, right? This would just be like our inclined plane activity. So if I gave you a graph like this, and I said, what is the object's position at 4 seconds? Well, then you don't need to de-guess that. You would find it on the graph, and you would tell me the object's position at 4 seconds. But if it's something where, if I gave you a velocity time graph, and I said, what is the object's velocity at 4 seconds? Well, you'd get it. And then if I said, well, given that, what is the object's position at 8 seconds or something like that, then you might need to use some DGuess for that sort of thing. If it requires you to actually do some number crunching, then yes, use DGuess. If it doesn't require number crunching, if it's just, do you know how to do this thing? Like, do you know how to read a graph? Do you know this fact, I guess? Then you don't need to use DGuess.
Even for simple ones like F equals MA, do we have to do the whole DGuess process, or just plug in like 2 numbers?
I would really suggest you do, because if you screw it up, you're gonna be in a sorry state. If I can at least see your thinking process, and if you're thinking through most of it right, I can give you a little bit of credit. But if there's a situation where you need to use FNet equals MA, and you're just rushing through it to get a value for net force or acceleration or whatever you need to be solving for, if you do it wrong, I can't give you anything. So I would really suggest for all of your calculations on the lab practical, because the final exam is all multiple choice, so I don't need to see any work on the final. But for the lab practical, I would really suggest, if you can show work, show work. It's just to help you. I really don't care, but you could be punting 25% of all your points just because you're not showing me any work.
So do we have to follow it exactly, or like we don't have to write out devious?
No, but you should follow that process. You know, whether you're giving me a really basic diagram, most of the time, like for forces, your diagram is just your free body diagram. Just showing me, you know, okay, I have a box, I have a force of gravity, I have a normal force, and I have an applied force. Okay, there's your diagram. Go from there. Because once you have your diagram, then you have a picture literally right in front of you of what's going on, and that's going to help you in situations like that.
But we have to draw out diagrams where we have calculations in it, like with exact forces, like 15.
That's possible.
So, like, instead of saying the applied force, you'd say...
Well, or you could say FA equals 12 newtons or something like that.
How would you find something? Like, say, you were having to put values on that. Like, for the force of gravity, would it be 9.8 newtons?
Nope. Force of gravity is going to be how much gravity affects that object, which is going to be your mass times 9.8 newtons per kilogram. That was something I was noticing a lot of students doing today. Force of gravity, F sub g, is not 9.8. This marker is probably on its way out as well. Let me grab a new one real quick. Your force of gravity is equal to your mass in kilograms times 9.8 newtons per 1 kilogram. We did a lab on this. Force of gravity is not 9.8. Your force of gravity is your mass times 9.8, if your mass is already in kilograms. But get familiar with dimensional analysis. If I give you a mass of well, no, let's not even do that. If I give you a mass of 600 grams, first you need to convert that to kilograms. So you're going to multiply by 1 kilogram over 1,000 grams. Then you're going to multiply by 9.8 newtons per kilogram. And if you took chemistry, you'll remember this. Your grams cancel. Kilograms cancel, you're left with newtons. That's what you want. You're going to have, what? 600 over 1,000 is going to be 0.6. 0.6 times 10 is going to be 6. 6 newtons, or probably, 5.9 or whatever. I don't care if you round to 10. That's fine. I think it even says on every single page of the test and the lab practical and the final. You can simplify g, or the acceleration due to gravity, from 9.8 to 10. I don't care which one you use. Yeah.
For the labs are due tomorrow.
Mm-hmm.
I never did. So does the weight on the hanging mass affect the acceleration of the cart?
That's the only thing that affects the acceleration of the cart. Yep, because, I guess the mass of your cart will affect its own acceleration. The more mass on your cart, the slower it's going to accelerate. But the only force that is affecting the acceleration of the cart is the hanging mass. The hanging weight is your net force.
Okay,
You
so
can draw that out if
yeah.
that doesn't make sense. If you do your force diagram, this totally makes sense. So here is my Atwood. Here is my cart with the string and the hanging mass. Now, if I isolate my cart, I'm going to draw a force diagram for my cart. I've got force gravity down. I have force normal up. I have force tension out. I'm going to do the same thing with my hanging mass. Force tension up. Force gravity down. I know that this is going to fall down, right? So I'm going to draw A over here. I have an acceleration down. I know that tension is always the same at all points along a string. You might have had this reinforced today in the back when you were pulling the two force probes with the string. No matter how you pull it, the force readings on each force probe is the same. The tension is the same at all points on that string. So this tension here is the same. Still the same. This tension is the same at all points in the string. So if this is accelerating down, our cart is going to accelerate to the right. They're going to experience the same acceleration because the only force accelerating the cart is tension. So what we're going to be looking at is F net equals MA. And really, what we're looking at here, I don't want to get too involved here, but I think the way there's a video on Power School that discusses this from, I think, Thursday or Friday that you can watch. And I'll make sure that that gets reinforced tomorrow so that students can watch it. But it talks about how we can actually use a variant of this equation. We turn this into F net equals mass of our system times A. So now, instead of looking at the mass of just one of our objects, we can look at the mass of our entire system. And that's going to help us determine the acceleration of our system. Because the acceleration of both blocks is going to be constant, or rather, the acceleration of the block and the cart are constant. So we can look at this in terms of the mass of our system. Yeah.
So we did force versus, or acceleration versus force, which is the hanging mass affects the acceleration. Like
if you did A versus F, then that is leaving your system mass constant. So yeah, that would be seeing how your net force affects your acceleration.
Which would be the changing the weight on the hanging mass.
Yes.
And then the other one was
changing the mass of the cart and leaving your hanging weight constant.
And what was the result for that one?
For that one, as you add more mass to the cart, the acceleration of the system decreases, right? If you increase the mass of your system but keep your net force the same,
so
acceleration is going to go down.
So is it a graph, like a square root type graph?
Yeah, your graph winds up looking like that. And then to linearize it, you do 1 over x, and then you get your straight line.
For our lab that's due tomorrow, do you want us to have a picture of both lab graphs?
Yes.
Do you want us to do an analysis of the data?
Yes.
Each one?
Mm-hmm. Yep. I think you need to be able to speak to what's going on in both of those situations, even if you didn't do it. The alternative would have been to have you do each of them, and that would have taken another 2 or 3 days. So I chose the slightly less painful option, where you just need to be responsible for the evaluation of the data.
And what is the equation for what's the one where it's like that column?
This?
Yeah.
This is an inverse relationship.
Yeah, but what's the name of that? So the other one's A versus F. What's this one called?
A versus M. Yeah, so you have A, and this is really like M.
Which lab did your group do?
A versus F.
This one?
Bottom one.
I did the top one. Can I give your groups data? I could share mine with yours. Or do you already have one?
I already have one. But I can...
Any other questions? That wasn't a question.
It's a statement. I know.
We've covered a little bit on waves. We hammered a lot of forces. So that might be helpful to anyone who's worried about the test on Wednesday. This will get posted to YouTube immediately after, and maybe some students will watch it tomorrow, but I'll let people know in class that we covered a lot of stuff on forces today.
Yeah, because that's what I was kind of coming back from break and then
Yeah.
I forgot about the...
Yeah, like I said, 9 days off, that's a heck of a time for students. I know how difficult that is, and I'm not even blaming you. It's just really hard.
Like, I felt like I didn't know what I was... I felt like I didn't know what I didn't know.
Yep. That echoes what I've heard from a lot of students. Anything else real quick?
I think I'm good.
We're good? Okay, then that's going to be it. I'll shut her down. No one joined us with any questions from the interwebs, so
What's your email?
calling it. All right, that's all she wrote. A little less than an hour today.